Today I'll be walking you through a brief introduction and demo of the TrustInSoft Analyzer. The focus of the analyzer is on detecting undefined behaviors, and this is something straight out of the C and the C++ spec. An undefined behavior is complex to detect issue in code that you likely know as a buffer overflow, access out of bounds, use after free. There are literally hundreds of undefined behaviors, but they are all serious issues that often need resolving in the interest of security, safety, and reliability in code. The unique thing about the analyzer is a focus on those bugs that matter. So tracking and identifying those undefined behaviors in your C and C++ code is an extremely difficult problem in the industry. There are often subtle conditions which cause them to manifest that may go unnoticed with traditional testing in your code. And this is what typically leads attackers to exploit them in the wild. Having an undefined behavior in your code certainly represents an increase in attack surface and risk, but it also could potentially compromise the reliability of your code. And in mission critical applications, that's simply not acceptable. The other unique thing about the analyzer is the fact that it is a sound tool thanks to formal methods. And this is a unique approach in the industry where we're leveraging abstract interpretation amongst other formal methods in order to analyze code for undefined behaviors to provide a mathematical guarantee of the absence of undefined behaviors when in fact you've eliminated them all. And that's unique in the industry against both static as well as dynamic analyzers, which are semantically driven or using rules engines to identify issues in code. When those tools are run and they say that they don't detect anything, that's just representative of the fact that their rules engines haven't been updated or potentially are not exhaustive enough to cover all of the situations which may exist in your code. In other words, there's no guarantee that there is no issue in your code, only a guarantee that that version of that rules engine or that database hasn't identified any in your code. The unique thing about the TrustInSoft Analyzer is when it says that there are no undefined behaviors detected, that's mathematical proof, a mathematical guarantee of the absence of undefined behaviors, which means that unless or until you change your code, there are no undefined behaviors that are there that are potentially exploitable or are going to cause you an issue after you ship that code. The other thing that's unique about the analyzer is it's very easy to get started. I'm about to show you in the demo, as well as a follow-on slide here, what are the different modes and models of operation of the analyzer. It's very easy to get started, leveraging your existing tests and then moving up into what we call a level 2 and ultimately a level 3 analysis. And then finally, there's the ultra-precise target emulation. There's no need to have the physical target or other instrumentation when you use the TrustInSoft Analyzer. You can configure the analyzer to emulate your CPU type, your word size, endianness, padding, memory mappings, and alignment so that you can start your testing at this level much earlier in your development cycle than you otherwise would be able to. You don't need to wait for, let alone run on that hardware or that architecture. These are the three modes of operation of the analyzer. As you can see here, we start at what we call level 1 analysis, where we can replay your existing tests without modification. It is very quick and simple to get started. The analyzer will apply its own assertions here at this level to find additional or undetected, undefined behaviors, even by just merely running your existing tests, no modifications. Extremely simple to get started. Where a lot of customers ultimately want to get to and where the bulk of the power is in level 2. It's input generalization, the ability to test ranges of all integers, all strings, all data types as inputs to your code and still achieve that mathematically proven result of the absence of undefined behaviors, or in fact find conditions that you never knew existed before in your code in order to suss out undefined behaviors and ultimately eliminate them. The third level of operation is functional proof, and this is outside of the scope of our introductory demos, but is something that we would be happy to set up with you and talk through, which is leveraging ACSL or Axel specifications to define how the function should behave, and the analyzer can validate that in addition to checking for the presence or absence of undefined behaviors. And that's important when you do have a requirement for a functional spec that tells you how the code should behave, what are the expected outputs and possible ranges and bounds above and beyond merely just the presence or the absence of undefined behaviors. And that functional proof is something we've helped many customers provide for regulatory and compliance and other peace of mind reasons. And with that, let's move to the demo. What I have here for my demo begins with just a very simple single function. It's called increment array. It takes as its inputs an integer array and the length of that array. And it loops through each element of that array and it increments it by 1. We also have a handful of test drivers for this function, which is similar to how the majority of customers we work with will have tests and test functions, unit tests even, that they're running against their existing code. There are 4 tests here. There's a small array test where we'll test this function with a handful of small integer values. Then we will try to be more exhaustive. We'll test it with a randomized 1,000 integers. And then we'll corner case check it for a few different possible foreseeable issues, like what if the array is 0 length, or what if it's uninitialized in the null test. And many customers are doing versions of this where they'll say, let's run those tests. And as you can see here, no TrustInSoft Analyzer involved at this point. Those 4 tests are running. Each one is passing. You can see the previous before and after views here so that you can see the integers did get incremented. And also, by the way, we have 100% code coverage. Those 8 lines are all being exercised as a result of running these tests. And we commonly start working with customers who have some code, and they may even have some tests like this, and they want to get started leveraging the TrustInSoft Analyzer. And so in order to show you what that would look like, I'm going to run those 4 tests again, but I'm going to invoke them through the TrustInSoft Analyzer rather than running them independently like I just did. And this is a level 1 analysis that we run through the TrustInSoft Analyzer. You can see it is very CLI driven. There is an interface that I'll show you here in a later step, but it's not required. This allows for nice, clean integration with various CI/CD platforms and pipelines and workflows, which is nice. There's also an HTML report that gets built up from all the multiple JSON outputs of the analyzer. And as you can already start to see in that CLI output, there are, in fact, undefined behaviors that were lurking in our code that were going undetected or unnoticed through as a result of the execution of those 4 previous tests. In fact, it's the same undefined behavior that affects both the small and the large array case here. And it's just a simple error, a common mistake, where we're reading 1 past the length of the array here. You can see that there's a predicate that says, is the array valid or not? We're reading past the length of that array. Because we're in this checkup here, we have a while length is greater than or equal to 0, and it should merely just say while greater than 0. This is something that wasn't being expressed as a result of running those previous tests and does represent an undefined behavior that we will certainly want to eliminate. The fix, of course, is, like I mentioned, to go back to our code and eliminate that equal sign. So now we'll just do while greater than 0. We can rerun our existing test without modification. Again, still just a level 1 analysis through the analyzer in order to see if additional undefined behaviors can be detected or if we achieve a clean result here. You'll notice in the CLI output, all of the results are displayed. We'll also have that report, which will automatically pop up at the conclusion of this analysis run here. That's an option. And this report will give us great insight into not only the quality of the code, but also the function and code coverage. You can see we have MCDC coverage, statement coverage, line coverage, and a variety of those outputs, all even on the summary here. Moving over to the individual analysis again, no undefined behavior found in the program. This is a significant result, and this is what I was talking about in the introduction earlier. When the analyzer says no undefined behavior found, that's active confirmation of the absence of undefined behaviors for the discrete input values that we used in this test. And that's the crucial point or thing to remember as we move now from a level 1 analysis to a level 2 analysis with generalized inputs. It's excellent that we're able to achieve a result like this, where we can say with confidence, no undefined behavior found for those input values. But that last asterisk is concerning. We would ultimately want to be able to say there are no undefined behaviors for any inputs. But how would you otherwise achieve that? Or how could you do that with traditional means or other tooling? It's virtually impossible. You would have to resort to fuzzing and intelligent algorithms and other things in order to build up your confidence that you've tested enough inputs, probably not all exhaustive possible inputs, but enough that you have confidence that you may have found all of the undefined behaviors that exist. But what I'm about to show you is running the analyzer at level 2, we can provide active confirmation of the absence of undefined behaviors for any input value. And let me show you what that actually looks like. When I invoke the analyzer next here at level 2, we'll rerun those same previous 4 tests, but we'll introduce a 5th test now that we've written here called test generalized array. And you'll notice here we initialize 1,000 integers in an array, but we take advantage now of a function called tistMakeUnknown. And what this function does is it allows us to test the range of all possible integer values up to 1,000 integers long in that array. And you can see in the comments there the math behind how many unique tests that what we're about to do represents. And think about the time it would take to run this in practical code, which is infinitely more complex than what you're about to see here even. And it's just impractical. It takes too much time, too much compute resource, and just too much man hours really in order to make this practical. But what you're about to see here is the speed at which the analyzer takes advantage of this approach. We'll invoke it at level 2. Those previous 4 tests, by the way, will continue to pass. Remember, when we say mathematical confirmation of the absence of undefined behaviors, unless or until that code changes, these will just continue to pass. And that's a good thing. That's predictability. However, there's a new issue that's been detected as a result of running the generalized input, a lurking undefined behavior that was going undetected as the result of our previous tests using discrete input values. And as you can see here and notice, what the system is telling you in the report here is there's no protection in this function against the possibility that one of these integers in this array comes in at the int max for my architecture, and we try to increment it. We all know this as an integer overflow situation, which is bad. The tool is telling you also here what is the value, or the int max, where we discovered this issue. Remember, we didn't have to type that value in. It was tested as a result of abstract interpretation and formal methods, much the same way as we would test all other values of those integers. And as an anecdotal story, I'll tell you that while this may appear to be a really simplistic example, we see all the time situations where there are complex mathematical operations in functions where a very specific set of values in the variables will lead to a division by 0, for instance. And it's extremely difficult to find that if you're not able to test for all possible input values, like we just did with the analyzer here, to give you another practical example of when this is useful or the types of things that we can detect. Now, before I fix this and show you how the analyzer can provide a mathematical guarantee of the absence of undefined behaviors at level 2, I wanted to take a moment and highlight the user interface. Everything you've seen so far is CLI driven. The HTML report is separate and secondary. There is a wealth of information and detail in the JSON output. But what if this problem is particularly complex or can't be readily detected or understood by reviewing the report? That's where the interface comes in handy. And what I did to invoke that was just append the dash GUI on that command. And you can see the results are available. But instead of a report, I have now the interface of the TrustInSoft Analyzer. And this interface is extremely powerful. It shows you on the right your code under test, a highlighted line where the issue has been detected. In the center is the analyzer's view of the code, along with the bright red indication that there's a signed overflow issue here. And there's the value again that we saw in the report, and it's telling you here. But the power of this analyzer is in understanding the call chain. How did we come to this point in the code? Now, our function under test here is extremely simple. There is no call chain. But in more complex code and other examples where the call chain is sophisticated or the problem is millions of lines of code away from the symptom, you can use the analyzer to walk back and to understand that and to be prescriptive about your understanding of not only the problem, but in identifying the solution as well. So there's a powerful interface here that developers can use in order to troubleshoot and understand the issues in their code to a great level of detail. Like I mentioned, though, in our case, the issue is clear. And so we can come back, revisit our code, and make that correction. The issue, like we talked about, is the fact that there's no check in here like this, where it says if the value is less than int max, then increment. Otherwise, don't. And now if I rerun that analysis at level 2 again, we'll see if there are additional undefined behaviors or if, in fact, we can achieve a mathematically guaranteed clean result, as, in fact, we just have. So you'll notice that only took a few seconds, and now we have a mathematical guarantee within that function for the absence of undefined behaviors for any inputs in those integer positions up to 1,000 integers long. This is a result that is extremely difficult, if not impossible, to obtain in any other way. And the unique strength of the analyzer is this. It's in the proof here that tells you you are done. Unless or until that code changes, no buffer overflows, no use after freeze, none of those crashing critical security vulnerabilities that we all fear may lurk in code. And it's that sort of reliability with confidence and proof in the reporting and the output details that TrustInSoft is known for and that TrustInSoft can bring to your code. Thank you.